You ever just look up at the stars and think, man, we're really stuck here, aren't we?
Uh-huh. Yeah. That feeling.
The distances, I mean, to other stars or like the edge of the galaxy, it's just mind-boggling. Makes you wonder if we'll ever really get out there. How do you even start thinking about trips that huge?
Well, that sense of awe, that challenge, that's exactly what drives science, right? You hit the nail on the head. Our current rockets, chemical rockets, they just don't have the juice for interstellar travel. Not really.
Which, yeah, brings us neatly into today's deep dive. We've got some really interesting sources here looking at a potential, well, a total game changer for rockets.
Something that still feels a bit sci-fi.
Totally. Antimatter rockets. Now, for anyone listening, the whole idea of using antimatter for propulsion, it probably sounds pretty wild.
And look, it is definitely cutting-edge stuff, no question.
Right.
But the basic physics behind it, that's actually pretty solid, well-understood stuff. So our mission today, basically, is to unpack what antimatter actually is. And how its weird properties could, theoretically let us travel way, way faster.
And also touch on the massive hurdles involved.
Oh, yeah. Definitely the hurdles. But also why scientists are still so fascinated by it, despite those challenges.
Think of this as your kind of quick guide to the essentials, no getting bogged down.
Exactly. We'll hit the highlights from the material we looked at.
Yeah, the sources we have really lay out both the incredible promise and, let's be honest, the daunting reality of this stuff.
It's quite the contrast.
So let's jump in. What is this antimatter stuff, and why is it potentially so revolutionary for getting around space?
Okay, so fundamentally, antimatter is like the mirror image of regular matter, the stuff that makes up you, me, this microphone, everything.
A mirror image?
Yeah. So for every particle we know, like an electron, there's an antiparticle.
Yeah.
Same mass, but the opposite electric charge. So the electron is negative, it's antiparticle, the positron is positive.
Right.
Same deal for protons, positive charge. They have antiprotons, which are negative.
Right, like a photonegative at the particle level?
Kinda, yeah. A flipped version.
So it's flipped. But what makes it so powerful? What's the, the big deal?
Well, that's the key. What happens when matter and antimatter actually touch?
Okay.
They don't just bump into each other.
Okay.
They annihilate. Gone. Poof.
Yeah.
Their entire mass gets converted directly into pure energy. And that conversion follows Einstein's famous equation, EMC4.
The classic. So it's not like burning fuel where you're just rearranging atoms.
Exactly. Chemical reactions, even nuclear reactions, only release a tiny fraction of the mass as energy. Annihilation. It converts all the mass. 100%.
Okay, wow. So the energy release must be huge.
Unbelievably huge. The energy density is just staggering.
Oh.
The sources we looked at give a figure 1 gram of antimatter meaning 1 gram of matter.
Yeah.
Releases of 90 terajoules of energy.
90 terajoules. That sounds like a lot. How much is that in like real terms?
Okay, put it this way. That's roughly the energy of 21 kilotons of TNT.
Wait, 21 kilotons? From 2 grams, 1 gram of each.
Yeah.
That's enormous. That's like a small nuclear bomb, isn't it?
Pretty much, yeah. It dwarfs chemical energy, dwarfs even nuclear fission or fusion by mass.
Okay. I'm starting to see the appeal for rockets now.
Right. So the idea is even tiny amounts, like milligrams of antimatter, theoretically that could be enough energy to power a ship across interstellar distances.
Pilgrims for interstellar travel.
Wow.
That's a game changer. So, okay, how would you actually use that energy? How does it make a rocket go?
Right. So the core concept is controlling that annihilation carefully and then directing the energy outwards to get thrust.
Okay.
And the sources we reviewed outline a couple of main ways people are thinking about this. The first one is often called direct drive.
Direct drive. Okay. Sounds straightforward enough. What's the idea?
Well, you'd feed tiny controlled amounts of antimatter into a reaction chamber, let it annihilate with some normal matter in there. The massive energy release then superheats a propellant, maybe something like hydrogen, to insane temperature.
Right.
And then you blast that superheated propellant out a nozzle, just like a regular rocket, basically, but with way, way more energy heating the exhaust.
So antimatter is the ultimate heater for the propellant.
Got it. What's the other main approach mentioned?
The other big idea is, well, it's even more ambitious. It's called the photon rocket.
Photon rocket. Exactly. The annihilation produces gamma rays, super high energy photons, a form of light.
Yeah.
The idea here is to somehow harness those gamma rays directly. Use the light itself as your thrust.
Wow. A rocket pushed by light beams. That sounds very sci-fi. What's the catch?
The catch is huge. As the sources stress, Gamma rays are incredibly energetic, trying to reflect or focus them with any material we know how to make. Extremely difficult. Think about it. These things are way more penetrating than even X-rays. They'd mostly just go straight through any mirror you tried to build.
Ah, okay. Yeah, that makes sense. You can't really bounce gamma rays easily.
Not with current tech, no. It's a massive materials science problem.
Okay. Now, the sources also mentioned something else. ACMF, antimatter catalyzed microfusion. What's that about?
Right, the ACMF. That's kind of a hybrid idea.
Hybrid.
Yeah. Instead of using antimatter as the main fuel source, you use tiny amounts of it as a trigger.
A trigger for what?
To start nuclear fusion reactions. You'd zap a pellet of fusion fuel with a tiny bit of antimatter. The annihilation energy provides the spark needed to get the fusion going.
Ah, I see. So like using an antimatter matchstick to light a fusion fire.
Exactly. It's a pretty good analogy.
Yeah.
The fusion releases much more energy overall, but you need that antimatter kick to start it efficiently.
That sounds maybe a bit more achievable than the pure photon rocket.
Potentially.
Yeah.
It's seen as maybe an intermediate step. But look, whichever method you're talking about, direct drive, photon, ACMF, the performance improvement over chemical rockets is just revolutionary.
How much better are we talking?
We measure rocket efficiency with something called specific impulse, ISP. Think of it like fuel efficiency, miles per gallon,
Yeah.
but for rockets.
Okay.
Today's best chemical rockets, they top out around, say, 450 seconds of ISP.
450. Got it. And antimatter.
The theoretical numbers we saw in the sources, they range from maybe 10,000 seconds up to potentially 1 million seconds.
Wait, 10,000 to 1 million compared to 450.
Yeah. It's not just a little better. It's orders of magnitude better.
Wow.
Yeah,
That changes everything, doesn't it? Mission times, how much stuff you can carry,
Yeah.
where you can even think about going.
Completely transforms the possibilities, yeah.
Okay. The upside is clearly massive. Mind-blowing even. But you mentioned hurdles, big hurdles. This all sounds very theoretical right now. What's stopping us? What are the major roadblocks?
Yeah. There are some very significant challenges, maybe the biggest one.
Sure.
Just making the antimatter in the first place.
Production.
Exactly. The sources are really clear on this. Producing antimatter with today's tech, using things like particle accelerators, it's unbelievably expensive.
Oh, expensive.
We're talking, estimates are in the trillions of dollars per gram.
Trillions. With a T for 1 gram.
Yeah, trillions. And it's incredibly slow, too.
Yeah.
Making even that 1 gram could take, well, decades, maybe longer, with current facilities.
Wow. Okay, that price tag alone is pretty staggering. One source mentions CERN produces maybe 10 nanograms of positrons a year. Nanograms.
Precisely. A nanogram is a billionth of a gram.
Yeah.
It just shows you the scale of the problem. We need milligrams or grams for rockets, and we're making nanograms per year.
Yikes. Okay, so production is hurdle number 1. What else?
Hurdle number 2, storage.
Right, you said it annihilates on contact.
Instantly. With any normal matter. So you can't just put it in a tank like rocket fuel.
So how do you store it?
You need perfect isolation. Basically, a perfect vacuum chamber. And then you use complex magnetic and electric fields. A penning trap is one type to hold the charged antiparticles suspended in the middle, making sure they never, ever touch the container walls.
So it's floating in nothing, held by magnets.
Pretty much. And keeping that stable, especially for long space missions, in the vibrations and environment of space. It's a huge engineering challenge. It's like trying to carry smoke in a sieve.
Okay, incredibly expensive to make, almost impossible to store safely. I'm guessing using it isn't exactly safe either, all that energy release?
You guess right. That annihilation process. It doesn't just produce heat or light. It produces intense gamma radiation and other high-energy particles, too.
Gamma rays. That's bad news for people, right? And electronics.
Very bad news. You'd need massive amounts of radiation shielding to protect the crew, to protect the spacecraft systems, and shielding is heavy.
So that adds weight and complexity back into the ship design.
Absolutely. It's a major engineering headache on top of everything else.
Okay, so let's recap the problems. Costs trillions per gram to make. Takes forever. Needs incredibly complex magnetic bottles to store. And it blasts out deadly radiation when you use it.
That about sums up the big ones, yeah.
Which kind of makes you wonder, why bother? With all that stacked against it, why does this idea of antimatter rockets still have such a grip? Why does it keep inspiring people?
That's the fascinating part, isn't it? Despite all those, frankly, enormous obstacles, the potential payoff is just so immense, it's transformative.
Like what's the biggest draw?
Interstellar travel, that's the holy grail.
Right, getting to other stars.
Exactly. If we could actually build these things, even reaching a fraction of the speeds they theoretically allow,
Mm-hmm.
we're talking about relativistic speeds, significant fractions of the speed of light,
Mm-hmm.
journeys to the nearest star system, Alpha Centauri, it's about 4.3 light years away.
Mm-hmm.
Instead of taking tens of thousands of years with current tech, maybe it becomes possible in decades, maybe even within a human lifetime.
Reaching another star in decades, yeah, that changes humanity's place in the universe, doesn't it?
Fundamentally, the possibility of exploring other solar systems, maybe finding life, it opens up everything.
It really does. But is it just about travel? Or are there other reasons?
Oh, definitely other reasons.
Yeah.
Just studying antimatter, trying to figure out how to produce it, store it, manipulate it. That research could unlock some really deep secrets about the universe itself.
Like what kind of secrets?
Well, one of the biggest puzzles in physics, in cosmology, is the matter-antimatter asymmetry.
Meaning?
Meaning, why is there so much matter around us and seemingly so little antimatter? According to the Big Bang Theory, they should have been created in equal amounts. So where did all the antimatter go?
Ah, right. I've heard about that. A big mystery.
Exactly. Understanding antimatter better could give us clues about the very beginning of the universe, how everything evolved. It tackles fundamental questions.
So even if the rockets themselves are a long way off, the science along the way could be groundbreaking on its own.
Precisely.
Yeah.
And there could be more, let's say, near-term benefits, too.
Oh, yeah.
Yeah, the technologies you'd need to develop for antimatter rockets, better ways to trap particles, manipulate energy that could spin off into other fields.
Like?
Well, these sources mention things like potentially more efficient energy systems down the line, maybe breakthroughs in medical imaging. You know, PET scans already use positrons, a type of antimatter.
Oh, right. PET scans. I didn't realize that was antimatter.
Yep. So advances could lead to better diagnostics or treatments. And of course, just fundamental particle physics research benefits hugely.
So it's not just about the rockets. It's about pushing science and tech forward across the board.
You got it. It forces us to tackle problems at the very edge of our capabilities.
Okay, so we've gone through the science, the mind-blowing potential, and the, frankly, terrifying challenges of antimatter rockets.
Quite a journey.
It really brings us back to where we started, doesn't it? Given how incredibly difficult this all is, should we really keep pouring resources and hope into this? Is it a realistic future for space travel or just a sci-fi dream?
That really is the billion or maybe trillion-dollar question, isn't it?
Right. Yeah.
Look, nobody thinks building an antimatter starship is right around the corner. The practical hurdles are immense. We can't pretend they're not.
Right.
But the potential rewards,
Yeah.
reaching the stars, unlocking cosmic secrets, they're just so profound. You could argue that continuing the research, even just the basic science, is, well, not just worthwhile, but maybe essential.
Investing in the long, long game.
Exactly. It's about exploring those potentially revolutionary paths, even if they look incredibly steep right now, is how breakthroughs happen eventually.
Well, it definitely gives you a lot to chew on. Okay, here's a final thought to leave everyone with.
Yeah.
Something to ponder. Let's say, just imagine, antimatter propulsion does become real. Against all odds, we figure it out. We suddenly have the ability to travel, maybe not just to the nearest stars, but way out towards the edge of our galaxy.
Okay.
What kind of unexpected things might we find out there? What completely new challenges, things we can't even conceive of now, might be waiting in those really deep, unexplored parts of the cosmos?
That's a big question. What's beyond the next horizon and the one after that?
It makes you realize how little we actually know.
Truly thought-provoking. It highlights both the infinite possibilities and maybe the infinite unknowns that come with pushing boundaries that far.
Absolutely. You know, even the wildest ideas, the biggest leaps, they all start with someone imagining something that seems impossible today.
Well said.
And that drive, that human need to explore, to see what's out there, whether it's powered by kerosene or antimatter, that's not going away.
Hopefully not. Thanks for taking this deep dive with us today. It's been fascinating.
My pleasure. Lots to think about. Definitely. Until our next exploration, keep looking up and keep wondering.